All right, I think we're ready to go here. So today we are covering Copernicus, a little bit of history, Kepler, and the laws of planetary motion. An auditory lecture?
Yeah, because you don't have anything else for you.
Oh. There. And now I would like to share it with you. Okay. So for starters, Nicholas Copernicus is the first guy on the list, and Nicholas Copernicus with his with his mentor Tycho Brahe. In fact, it was this guy first, Tycho Brahe. Over the course of his lifetime, took amazingly accurate and meticulous notes on the positions of the planets in the night sky. And whenever he could see, so he would have his notebook out, and he would take what's it called? A compass, like a measuring compass that he could set like calipers. That's what you call calipers, and he would set the distance between them just right in his notebook, and then he would use those measurements later in knowing everything was proportional, okay, and just where everything lined up and where they were with respect to the sun and all the other planets, and where they were and when they were and at what time of year. And he just took all of these notes, but he didn't really do anything with them. He was one of those, wasn't really next level. He was just very meticulous and very interested in recording all of this data. Okay, his student, however, Nicholas Copernicus, Nicholas Copernicus came along and took this data once Brahe passed away, and painstakingly took this data and made the calculations necessary to show that the Earth was actually going around the sun rather than the sun going around the Earth. And instead of there being the solar system used to be considered traveling where there would be the Earth. All right, so we'll have this. The Earth is in the center, and then around the Earth, everything, right, this is the geocentric theory, that everything would be traveling around, the Earth. But the sun stayed on a circular path, as did the moon. They were right about the moon. Okay, they knew that the moon actually did go around the Earth. They were right on that one. The sun, however, they thought also went around the Earth, and it was also in a perfect circle. They thought they were all perfect circles. The other planets, however, not so much. They knew that the next closest one was Mars. Okay, it looked pretty red to them, although it's more of an orangish. But, however, in fact, I shouldn't have drawn that. The problem with the other planets is when they go across the sky, there's a short period of time where they go backwards in their path and then come forward again. And it was called retrograde motion. And they couldn't explain it with the original geocentric theory, geocentric theory of planetary motion. So what they did is they attached a center of orbit, and then around that center of orbit, they had what's called an epicycle. And the planet was on the epicycle. And the epicycle would would circle the Earth. So as it went around, so Mars would kind of go like this. Okay. Imagine having to calculate that by hand. That is a colossal pain in the butt. Yeah? But it did explain, every so often, the retrograde motion, that as it traveled across the sky, it would go back and then forward. You guys follow that? Okay. Every other planet aside from the sun and the moon did this. Okay. And then there were like Jupiter's moons. Right? And Jupiter has 4 moons that are actually visible with the naked eye or with binoculars around it. And so you could see, the next orbit out, or another big orbit out, would be Jupiter. And so it would have its epicycles. And then around that planet, it would have other moons orbiting around the Jupiter with Jupiter. Luckily, 'twas not the way it actually worked. And after Copernicus, who said this is all nonsense, and showed that everything went around the sun, using Brahe's data, but he was actually the one that proved the heliocentric theory. However, after the heliocentric theory came Johannes Kepler, and Kepler took the Copernican system, the heliocentric Copernican system, and applied Newton's laws, because those had now been making. So we're talking early 1700s now, after Newton had published his what's called the Principia Mathematica, which is where he published his laws of motion. And Kepler, using Newton's laws and the Copernican heliocentric system, came up with his 3 planetary laws of motion. Okay. Number 1, satellites orbit their planet or their star or whatever satellite is orbiting, okay. They orbit in elliptical paths, okay, with the other satellite or the other planet or the other star or the partner at one of the foci. Okay. So the moon travels in an elliptical orbit around the Earth, and the Earth is at one of the is on a focus of that ellipse. You guys remember the foci of ellipses? You guys have done your. You guys know I'm getting nothing from you guys. I'm getting no recognition. Have you guys studied ellipses?
Yes.
Okay, where we have the general form x squared over a squared plus y squared over b squared equals essentially r, some r squared, right? Okay, and then this is the length. No, actually, I'm sorry, it equals 1. Equals 1. And then you have the longer one is the major axis and the smaller one is the minor axis.
Yes.
Okay. That's important. Okay. Rule number 2 is that planets in orbital motion Planets in orbit sweep out equal areas in equal times. So I'm going to try and draw this one by hand here, and it's not... It's much easier to draw a circle than an ellipse. Okay, so here's one of the foci. That means that as it travels from here to here, that this area right here, this dA, right, the change in the area, okay, or call it delta A, that the delta A over delta T, the time it takes to travel out this area, yeah, is equal to this area. That this area that it sweeps out here is equal to this area that it sweeps out over here. They can be roughly estimated as triangles. Okay. So what does that tell you about the motion of what's going on here? If you have a planet over here, let's say this is the sun, and here's a planet, what can you tell me about the planet that's orbiting over here as opposed to where it's orbiting over here? What is it doing over here?
It's going faster.
Yeah. It's traveling faster over here than it is out here, because the amount of time, it's only going to go that far in the amount of time. The area it sweeps out is the same, but it's going to go slowly through it because you have this long distance from. And then over here, it's going to go a lot faster because it's to sweep out the same area. It has, but it's shorter. It's closer to the sun, so it has to sweep. It has to go past it faster for this to work. You guys follow that? Yep. Okay. And then law number 3 is that the orbital period, that the square of the orbital period is proportional to the cube of the semi-major axis. Or in other words, the long end of your ellipse okay, so we'll call this that's 2A and that's 2B. So the semi-major axis is half of the length of the long way across the ellipse. We'll call that A. So the period squared is proportional. I'm sorry? Center the paper. Oh, I got you. That the square of the period, in other words, the time squared, the time it takes to go all the way around, squared, is proportional to the cube of this. It's like a radius. Think of it like a radius, except it's the long radius rather than the short radius. Okay, it's this distance here. This is the semi-major. This is the semi-major axis. Okay, these are Kepler's laws, and these are what govern our planetary motion. These still hold true today. But there's no Einsteinian adjustment to it. There's no quantum. All of our modern physics has done nothing to affect these. These all still hold as true as they ever have. If we start to find, in fact, fluctuations in these are how we find the existence of other planets or other massive objects in the system. In fact, NASA has recently revealed that somewhere out there is a 9th now, because Pluto's not a planet, a 9th massive planet out there that is beyond, or it is out in the Oort cloud, which is the where all the comets come from out there. There's one out there. We haven't located it yet. It's dark, but it's big, because we've been able to detect fluctuations in the orbits of our outer planets by them not quite being right on to these. So, what's that? Yes. And it's out there. Because we have instruments now to be able to detect the fluctuations in the orbits enough to be able to predict that there's something else out there. Okay. So, these are Kepler's laws. We've talked about the universal law of gravitation, which is how Kepler used the universal law of gravitation and Copernicus notes to come up with these. You should have enough to work on page 15, 17, and 18.